Okay. So, in the last lectures or the last couple of lectures, what we saw were designing of basic controller or compensating elements. The basic elements were a proportional element, a derivative element, an integral element, or a combination of proportional and a derivative, or a proportional and an integral control, or a combination of all of these three elements. And through some problems we saw, well, when can we add a PI, when can we not add a PI, what are the effects of adding just a proportional controller, what are the effects of adding just a derivative controller, and so on. And those problems gave us little idea of what happens actually when we try to design controllers. Do we do it blindly without worrying about stability or not, is what PI controller asks us to be careful of, right. The derivative control we saw aids us in the transient response of the system in case when a proportional control is not good enough to stabilize my system. Okay. So, what we will do here is to do a little further more analysis of those components. Okay. So, what we did so far is, well, just to sum up. So, we had a proportional element, a derivative element, and an integral element. The standard thing is just to be the objective being to track a certain reference at the output. So, well, proportional controller, it's well, what we saw was it very simple to implement, but it may not be able to meet some specifications. Sometimes it is not even good enough to stabilize the system. Stability, so when I look at proportional and the derivative control, we saw that it actually had a very good transient response. It could stabilize the systems, and then based on the value of the KD, which added damping into a simple second order system, it provides more control over where I should place my poles of the closed loop system. Integral control, well, it had perfect tracking of constant reference inputs, because it has a 0 adds a 0 at the origin, and I know that type 1 systems, if the reference signal is a step, then I could track it perfectly. And it also had good effect of rejection of constant disturbance inputs, where we saw that if the plant had some some poles at the origin, they were not good enough to neglect or reduce or reject the effect of disturbance. In that case, we actually needed to have a controller which had a pole at the origin, right. So, for second order systems, all these proportional, derivative, and integral control, they add to stability. I can also look at where to place the poles. Placing the poles, I know, has lot of effect on the relative stability of the system, perfect tracking of constant reference inputs, and also I could reject constant disturbances with the help of an integral control. Okay. So, what we will do here is to just get little more understanding of this integral and derivative actions, and what are the practical issues while I implement PID controllers. And this would lead us to some kind of approximation of these PID components called the lead and the lag compensation, right. And then of course, we will also look at these performance specifications both in the time and the frequency domain, and see how they actually connect to each other. Okay. So, let us start with a very basic first order system with a proportional controller. What do I usually want to do is to track a reference at the output. Okay. So, as long as A is greater than 0, I know that the system is stable and it will have a steady state value of y equal to 0, right, some response like this. And through a feedback controller, I just want to see if I could try to shift this steady state value to 1, right. For example, if I am just something is lying on the table, if I were to lift it, I will just need some external force, right. Can I just lift it to some 1 meter above the ground, right. So, here I will say through a feedback controller, can I try to shift the steady state position to 1. So, let us try to understand, does a proportional controller help me achieve this. So, what is the structure? So, I have the reference, I have the output, then the error goes via Kp, and the Up is Kp times Es, and this goes as an input to the controller and then generates an output. So, typically what I would like is E t should go to 0 as t goes to infinity, right, or the steady state error should be 0, or which means that this y should track this reference asymptotically, right. Okay. So, now let us just try to understand this with the help of the block diagram here, right. Okay. So, let us just see with this help of this block diagram. So, what do I want? I want E to go to 0 as t goes to infinity, or y to track r as time goes to infinity. Okay. Let us see how this propagates. So, once E goes to 0, then I will have that this is 0.5 times 0 and this is also 0. So, this will be 0. Okay. Now, what is this actually is? This actually is computed to be this one, which is actually 0. Now, if this is 0, I go back here and I compare this with this thing, I say, well, the error is actually not 0, right. So, there is actually a contradiction here. I cannot have the steady state error to be 0 and in this setting. It could be something else. I am not really worried about that something else. I am just worried about keeping my steady state error to 0 or y tracking r asymptotically, right, which means that if this was assumed to be true or if this was feasible, it would mean that this actual input to the plant would be 0.5 times 0 and the controller applies no input, right. Its natural state is 0. Without applying any input, I cannot get any output here, right. So, the controller applies no input to the system to maintain the system at the new steady state, which is contradiction, right, because if I were to hold this at some non-zero steady state, the controller must supply some input, right. The controller must apply some non-zero input to the plant to maintain the output at some non-zero value or a non-zero equilibrium, if I make also. Therefore, in this case the steady state error cannot be 0. We are only worried, is the steady state error 0 when I have a first order plant with a proportional controller in the closed loop tracking a step. Well, the answer is no. We also know those answers via the time domain analysis. We also know the answers via the error constants which we had found out. Okay. Now, let us say, well, I am not really worried about having a steady state error of 0, but some number. So, if I take this plant controller configuration, then I can compute that the error is 0.1, right. So, this is again follows the first order system analysis which earlier in the course, I think module 4 or something like that. Okay. Now let us see how is this consistent. So, there is a steady state error of 1, this error gets multiplied by 9 and I have input at input signal here as 0.9 and then the output because of this input will be 0.9 at steady state. So, I am holding this guy at 0.9, but to hold this guy at 0.9 I am actually having a non-zero input, right, which is actually also 0.9, right. So, I can with some adjustment of this guy reduce the steady state error, but of course, for the steady state error to go to 0, this has to go to infinity and again it will lead to some other contradictions. The steady state error will never go to 0, but we can reduce it to some small number depending on the choice of the Kp, right. So, the proportional controller, it reduces the steady state error, but does not eliminate it completely. Of course, there are practical issues of noise amplification and things like that. When I choose Kp to be very large, it may not be practically feasible sometimes and could come up with some other issues. Okay. So, can I add an integral control? Well, integral control would mean just add an integrator here. This would increase the type of the system to 1. And I know by the error constant analysis that a type 1 system, if I have a step here, I will track it perfectly, right. Okay. So, what does it mean again in terms of these signals, right. So, if I compute the error signal, well, the error is something like this and it goes to 0 asymptotically. Now, the input has some value like this, right. It is again it has some input value even at steady state, and based on this input value the output is tracking the reference asymptotically. So, up, this guy is now 1 over s times Et, or if I talk in terms of the time domain, it is the integral of the error, right. This signal you integrate it and you get up. Earlier it was just getting multiplied. If it was 0, it was 0.5 times 0, if it was 5, 0.5 times 5 and so on, right. So, the controller input is now the integral of the error signal, right, And when I do this, what I also observe is the controller output is non-zero. See, it's always non-zero. So, there are some points here the error goes to 0, error goes to 0 and whatever, but the control input is non-zero even though the error has gone to 0, right. Similarly, I could also show, we also did this in some problems earlier, that when there is a constant disturbance which could possibly come from here, the error due to disturbance accumulates and it is used to reject the effect of disturbance. Okay. So, in this case the output of the controller is the integral of the error. Okay. So, the controller output, which is the input to the plant, right, this guy is non-zero even though the error has gone to 0. You can see this here, right, here the error has gone to 0, the input to the plant is non-zero, right, and then for as it goes to 0 there is still some steady state value for the input, right. Similar analysis I could also do for the disturbance rejection as we had seen in some problems earlier. Okay. So, is that all? Is life now we see that just add an integrator and then steady state errors are gone? Well, it also comes with its own set of rules. So, what are the important points to observe when I have plant with integrators? When the plant already has an integrator, the integral control may not be necessary for steady state error, that we had also seen in the problems earlier, that I had a second order system, it was tracking a step signal perfectly asymptotically, right. So, and we also saw that the integrator in the plant does not help in disturbance rejection, right, and therefore, for this kind of scenarios I would need to have integral control via the compensator or the controller. Now, second thing is called the integral wind up phenomena. Now, this is a very practical issue, right. So, first is, well, these guys are not always stable, right. I have a pole at the origin, right, and if it could at best be marginally stable, right. And then not only that, when there is a limit on the actuation capability, let us say my actuation signal is some kind of force, right, which I cannot just apply infinite force, right. If I just buy an equipment which could give me some force, it is bounded by above and below by some values, right. And that phenomena is usually called as the actuator saturation, right. So, in this case, well, this is my controller input. So, this so the input to the controller from the error, it goes via this, and this UP is now has to go through some function like this, because my control action or my actuator has a limit here which does not allow the input force or the input voltage to go beyond a certain value. So, what happens here is that I may need, if I just roughly draw a graph, I may need an input which is somewhere here or an input which is somewhere here to drive the error to 0 or to meet some performance specifications and so on. But well, my controller via this actuator could just give me maybe 4 volts even though I need 10 volts, right. So, in this case what happens is that the integral, so there will be of course an error. So, I need 10 volts, but all I am getting is 4 volts. The error will still keep on accumulating and then the output could go to very large values, right. So, it does not really work in cases where I have some kind of an of a limitation in my actuator capabilities. So, that also I need to be careful of, right. Okay. We will not really discuss on how these kind of situations will be handled in practice, right, but it is good to know that it just that the integral control action, even though it looks extremely beautiful, it looks very simple, just 1 over S, it eliminates lots of steady state errors, it rejects disturbances, but it comes with two of this not really drawbacks, but some things which we should be careful of while we are designing a system. Okay. Also, what we could observe is that an integral control leads to sluggish closed loop response for a first order system. Okay. What does this mean? Let us just take a normal proportional controller and a plant as 1 over S plus 3. The root locus will tell me that as k increases, this guy just runs away to infinity. Okay. Now, if I add an integral control, which means I am adding a pole at the origin, then my root locus is like somewhere here, right, here and here. So, I am actually having my dominant, say for a larger value of k, I am somewhere here. If I just put the same value of k here, I might just end up somewhere here. Okay. So, this means that for that value of k where my pole without the integral action was say at -12 or -10 or somewhere in between, this response is faster than just having a poles or this complex poles at -1.5 plus minus j something, right, which means the response has become sluggish, which means my poles, or what I would now define as the dominant poles, are now closer to the origin, and that might, so here the systems might be oscillatory, here they are not oscillatory. Okay. So, and then if I look at higher order plants, they may lead to instability, as we had seen in the problems, right. So, we just had some cases where I just had j s square plus something times s plus 1, right. We had some constants here, right, and no matter what the values of the constants were, this system is always unstable, right. Okay. Now, what about the proportional plus derivative control action? The input to the plant now in terms of looks Kp plus Kds times Es, Kp times Et plus Kd times the derivative of the error, right. So, what we had seen earlier in the first lecture of this module was that a derivative control not only acts on the error, but also on the rate of change of the error, which improves the relative stability, right. So, we are adding a 0 to the open loop transfer function in the left half plane, and this 0 has the effect of pulling the root locus to the left, right, away from the imaginary axis in the stable region. Now, the more away I am from the imaginary axis, the more I can say that I am more and more relatively stable, right. And not only that, right, that the derivative term is, in some sense, it has some anticipatory effect or some anticipatory behavior. It predicts how fast the error is changing, and therefore, it could take corrective actions much better than if I would not have this E dot term. So, what is the effect of adding this proportional and derivative terms, right? So, we had seen this earlier in problems, but it is good for us to remind us every now and then. So, this j s square, if it just had a Kp without a Kd, I know that it is not stable, that the roots will always be on the imaginary axis. As soon as I add a Kd, I introduce a damping term, and by proper choice of this Kd, I could choose if the system is underdamped, overdamped, critically damped, and I can play around with the response of the system, right. Now, Kd influences only the s power 1 term, Kp influences s power 0 term, right. But then, well, to have control over the closed loop pole locations, I need two things, right. So, the standard thing was I had omega n square s square plus 2 zeta omega n s plus omega n square, and this omega n together with zeta characterize the complete behavior of the closed loop system, right. So, therefore, here both these terms Kp and Kd are necessary to have complete control over the closed loop poles. Okay. So, in the previous slides we had said that, well, the derivatives term is in some sense anticipatory or predictive, it can predict what is going to happen in the future, and these systems we called as non-causal systems. Moreover, while defining transfer functions, we said, or we defined a proper transfer function in such a way that the number of poles should be equal to the number of zeros, or the number of poles should be greater than the number of zeros. If the number of zeros were greater than the number of poles, as in this case there is 1 0 and no pole, these were improper transfer functions, and I could not realize or I would not be able to realize them in practice, right. Or I cannot just go to the market or say amazon.com and say, well, I am looking for a derivative control. No, that will not happen, right. And okay, amplification of noise. When I am looking at a derivative component here and say I have first like very high frequency noise, the effect of the derivative could be very bad in terms of the amplification of the noise, right. So, the derivative term acts on the rate of the error, right, and therefore, its output is highly susceptible to noise if it is changing or in a high frequency, and these noises can come either through the measurement sensors or through the reference signal itself. Okay. So, just for practical purposes, sometimes it is good for us to add the derivative control in the feedback loop if I have a low noise sensor, right. So, I can then I can reduce the effect of noise which are emanating through this, right. So, in this case the noisy reference signal gets filtered before or it gets filtered in the forward path before encountering the differentiator. It does not, the noisy signal does not really affect or encounter the differentiator, right. But of course, I still have to take care of the noise which is coming from y of s. That is a bit of a trade off here, but just some issues which we have to be careful of while dealing with these things in practice. Okay. So, the point is now, well, I have this derivative controller, I design nice properties, and I also told you that I cannot buy it in the market. Well, okay, so what do I do? Well, can I make an approximation? So, to address both issues, and I will tell you why I am addressing actually both of these issues, amplification of noise, and I can also take care of this non-causality. To address both these issues, I have an approximation of a PD controller now, right. So, in such a way that if you see here, I am just taking KDS, which is the actual derivative term, and I am adding a pole here, okay. And I do this S over P just to maintain the DC gain, okay. So, TDS is causal, I have one pole 1 0, okay. Now, and as P goes to infinity, TD goes to KDS and we recover the original derivative controller again, which is non-causal, okay. So, what does this guy do? 1 over S over P plus 1, this acts as a low pass filter, right, as we saw in that the frequency response, well, would go something like this, right, and you have some kind of bandwidth, right, a cutoff frequency as we had called. So, this multiplicative term acts as a low pass filter and eliminates high frequency content before passing through the differentiator, right, and usually noise is a high frequency signal. So, if I just add a additional pole here, that will take care of the high frequency signals, right. And of course, again as P goes to infinity, we have an all pass filter and we get back a pure differentiator. So, I have done two things here. I have made this guy to be causal or a realizable transfer function, okay. It still comes with its own set of it is still not done. And what we also saw is that I can place the poles further away from the origin. So, in one of the earlier lectures, we saw what is the effect of adding a pole to a transfer function, what is the effect of adding a 0 to a transfer function. If I add poles to further to the left, then the effect becomes small and small, right. So, I can smartly choose the location of poles such that the effect is like a derivative controller, it is causal, and it also eliminates this the issues related to amplification of noise, right. Okay. Now, this brings us to some kind of approximation of these PID controllers, which are in text referred to as lead and lag compensation. Okay. Now, let us start with a lag compensation, which essentially is an approximation of a proportional plus integral controller. A PI controller, well, I know, provides perfect tracking for constant reference inputs and helps in rejecting constant external disturbances. We have said this repeatedly, we will keep saying this over and over, right. Of course, this is not by itself stable, it has a pole at the origin, and so therefore, well, it is not a stable system. And we also saw we have this integral wind up property, and also in some cases we had seen for a higher order plants that it can actually destabilize the closed loop system. I add an integrator and I do the math, it says steady state error is 0, but say hold on, the system is actually unstable, you cannot apply the final value theorem blindly, right. So, now let me say take a condition where small steady state errors are acceptable, right. In that case, a perfect tracking may not be necessary, right. If I look at the cricket ball, I do this and it goes to, I do this, right, and it goes to the DRS, it's okay, right, even if the ball is hitting the stumps and if the margin of error is say 0.01 millimeter, I'm okay with that, right, it will still be the umpires call 3 reds or 3 greens and all those drama which adds up while we are watching cricket these days, right. In that case some small steady state errors are acceptable, right. Okay. Now these things leads us to the following approximation of a PI controller. So we start with the ideal one, which is Kp plus Ki over S, that is Ki over Kp plus S, but I just add not a pole at the origin, but very close to the origin, could be as much as 0.01, right, with P being very close to 0. Now the design procedure we will see how close to 0 it should be, right. So and further, well, this now looks like a gain K, a 0 and a pole in such a way that the pole is very close to the origin and some 0, right. This we will see how to design this, right, where K is Kp and Z is Ki over Kp, right. So the approximation of Pi, which is a lag compensator, what does it do? Instead of having a pole at the origin and see, this was a pole at the origin, a 0 on the left half plane. Now we have a pole and 0 both in the left half plane, right, and it is a stable controller, right, Z is less than 0, P is less than 0, it is always stable, and this approximation is called a lag compensator. Now we may ask ourselves, well, you are actually playing around too much with the system, right, you are teaching us something, but then you are approximating. Now we will see, is the effect of this approximation disastrous or is this good enough? Okay. So again we will start with the first order plant. I have this PI controller and the static position error, all this I do the error and I say, well, because of this integral action the steady state error goes to 0. Okay. Now consider the same plant with a lag compensator. This was the ideal one, right, which we said has very good properties in addition to some not very good properties too. Now if I do this K S plus Z S plus P and I pass it through my plant, I do all the error analysis, and what I get is that the steady state error is 1 over 1 plus K Z over P. This P is very small, 0.001 or 0.01, and say this, so based on these choices I can make this error as close to 0 as possible, right. Right. So this is not equal to 0, but this is, well, as close to 0 as possible, right. So that would be the objective, right. Okay. The steady state error will not be 0 with a lag compensator, right. However, what is in my control? I can have K, I have Z and I have P, and I can make this as large as possible to achieve as smaller errors as possible. Okay. Now what is the effect of adding the lag compensator on the root locus? Okay. So let me start with a plant. This is kind of fairly good looking. I have 2 poles and there is no 0, so everybody goes to infinity, and just by adding a proportional controller, well, I see the red line, right. So the poles are always at this complex conjugate poles, and then I have a certain steady state error. Sorry, this I could compute by hand. Okay. Now if I add a lag compensator, okay, first let us see what is the ideal case, right. The proportional plus integral controller, I do all these things and I get the steady state error to be 0, which theoretically I have been learning since a very long time now. Now if I, instead of this, I do something like this, I still have S plus 0.15 and I have a pole very close to the origin, that is like 0.015, right, and then the dominant closed loop poles are at this location, right, somewhere here, right, and then the steady state error instead of 0 is now 0.03, which is in a way kind of fairly acceptable, right. And if you look at the root locus, it does not really change much. So the qualitative behavior of the system with respect to gain has not changed much, if not at all. It will change by a very small margin, but will still be in a very safe zone, right. So I start with 0 and 0.03, this is okay, right. Okay. So what do these plots tell us, right. So I have a plot here with a P and a PI. So, and all the time while we were talking of PI, we were talking of perfect tracking, right, disturbance rejection. So all these are steady state behavior. These are all important at the steady state. Now, while I am playing around with the steady state behavior, or I am trying to improve the steady state behavior, does it have any bad influence on the transient behavior? So, the first plot, which is just adding the proportional controller and comparing it with the PI controller, you say, well, this is actually fairly close enough. So, there is not too much of compromise on my transient behavior, it will be very small, right. However, now this is the ideal PI controller. Now, I say, well, this is actually not very good, I need to actually go to something called a lag compensator, which is an approximation of a PI controller, and here I say, well, they are more or less they are very much the same, right. So much same that with this plot I cannot really find out any difference. If I zoom in like 100 times, possibly something would happen here, right. So, first thing is the PI controller has a good effect on the steady state performance without compromising too much on the transient behavior, and the PI is close to the lag compensator, and therefore, I can conclude that the lag compensator, if I implement it this way, it improves my steady state performance without compromising too much on the transient behavior. And so, that we will keep in mind whenever we are doing a steady state error design or a lag compensator design. Okay. Now, having found a causal approximation for a derivative controller, right, we would again like to do something similar as we did for the PI controller, right. So, under a similar approximation, so we will have again k, s plus z and s plus p, where again k I can find what are the constants and z and so on. Okay. Now, again this is causal, this is stable, and again which is less susceptible to high frequency noise, right, because it is not a pure derivative term, right. Okay. So, both the pole and 0 are in the left half plane with the pole further away from the origin than the 0. Now, we will really see why this is true, right. So, here it is so even though both the structures were the same k s plus z, k s plus p, here I also had the same structure, right. It really depends then on the choice of the poles and zeros to decide which one is a lead compensator, which one is a lag compensator, and I will shortly tell you that. But before that, let us again analyze what is the effect of adding a lead compensator on the root locus. So, what we saw earlier was adding a derivative component significantly improved my transient response without possibly much changing the steady state response. Okay. So, I start with 1 over s square, for which I saw that all the time that my poles how much ever I change the gain, they are just on the imaginary axis. Okay. Now, adding a proportional derivative control, which is I am just adding 0, it just has the effect, it just pulls the root locus to the left, right. So, the poles for a certain gain which were here, which were at this location have now become somewhere here, right, approximately, right. So, through this PD control and a smart choice of k and z, I can place my poles anywhere on this circle. The circle could be different for different kind of stuff, right. Okay. Okay. Now, look at this thing, right. So, this is desirable, right, that the root locus experiences a significant shift to the left, and shift to the left is required because I am interested in improving the transient performance. Now, this PD controller, how does it compare to when I just look at a lead compensator, which is an approximation, where say I have say a 0 at -1 here and a pole significantly further, right. Okay. Now, when I do this, well, you see that there is not much difference, right. The green line and the blue line are fairly close enough to each other, and again with some little adjustments here I can get my closed loop behavior to perform in a certain manner, right. So, what we conclude here is that the ideal PD controller, it affects or it improves the transient performance via this kind of a behavior, that it pulls the root locus to the left. It also helps in increasing the relative stability, but this approximation also does more or less the same kind of job, and this is realizable, this possibly is not, this is never realizable, right. And you can say, well, then what does this pole do, right? So, the only significant difference here is I have a S plus Z, but I have a pole. So, the reason I add a pole very further away is that the effect of pole as it goes further and further to the left, it reduces, right, as we had seen in the first lecture. So, I will add a pole to make it a proper transfer function, but I will keep it far enough in such a way that it does not really affect my behavior of the system, right. Okay. So, both compensators now have this structure S plus Z, it has a pole, it has a 0, it has a gain, right. So, when Z is greater than P, then it is a lag compensator. So, if I were just to write down in a very very nice way. So, the lag compensator should have an integral action, I just cannot have a pole at the origin. So, I place it somewhere very close by, okay, and then the 0 would be somewhere here, right. So, the 0 is to the left of the pole for a lag compensation. What did we see for the lead compensation is that if I add a 0 here, it pulls the root locus to the left, which is nice, which is what I want, right, it improves the transient response, but to make it realizable I have to add a pole. So, I add a pole further to the left, which means the effect of this on the transients will be as minimal as possible, right. And then of course, then we will see why these are called lead and lag, right. So, I will skip this discussion when we actually draw the Bode plots of these compensators. Okay. So, having had an approximation for both PD and PI, well, will there exist what about PID controllers, right. So, this problem is solved by using lead and lag compensators in cascade to each other, so as to approximate a PD control action, right. Okay. So, after all this design approximations to the lead and the lag and the PID being a cascade of a lead and a lag, how do we relate these to performance specifications? So, while we started our time response analysis, we said that the performance was based on the overshoot, it was based on the rise time, settling time, steady state error and so on. Then we also had an equivalent frequency domain analysis, where we talked of resonant frequency, we talked of bandwidth, and how are all these related to each other, and how are all these related to the design specifications, and how could we do this via a lead and a lag. So, before we do that, we will just compare the performance specifications both in the time and the frequency domain and see if they are actually related to each other. So, what we have done so far is found the description and specification of the closed loop in terms of the overshoot, as I said, the rise time, settling time, steady state error, and these were very nice to visualize, right. And this actually came across as finding all these were like second order system analysis, right. So, all these were nice when you say, well, there are several poles in the system, but if there is a dominant second order pole and maybe all other guys lying further to the left and maybe some zeros here, zeros here. So, this is what dictated my behavior of the closed loop system, right. So, all those analysis could be just made based on these dominant closed loop systems, right. So, however, we did not really talk much of relative stability, noise rejection, and these were nicer to understand in the frequency domain in terms of what we saw when I actually add integral component or a pole in my what was that, the lead compensator. It had a good effect, it had two good effects. One was it made the derivative controller look a little more realizable. It also had the effect of attenuation of high frequency signals, which are essentially the noise signals, right. So, and these are in some sense better to understand in the frequency domain, and therefore, we see sometimes these parameters or the design specifications are, well, to loosely speaking, simpler than in the time domain. Simpler not in terms of that the problems which I give in frequency domain are simpler than the time domain. It might actually turn out to be the reverse, that this might need a little more trial and error or some approximations than the design in the time domain. So, simplicity comes from just from one or two parameters I can actually get lots of information, right. So, before we do that, we just find out, is there a correlation between these parameters such as the rise time, overshoot to the frequency domain parameters, which were the resonant peak, the resonant frequency, bandwidth, the gain margin, phase margin and so on. Again, all our analysis for obvious reasons of the dominant pole behavior was, or we tried to find this correlation for second order systems, right. This correlation holds very nicely when the closed loop system has a pair of dominant poles, right. And for higher order systems where there is possibly no concept of this domination pole, we may have to do some better simulations to achieve other results. But for our analysis purpose, we just restrict ourselves to the dominant poles, and that also gives us lots of rich information. Okay. So, starting with a second order system, I know all these formulas now, well, possibly by heart, right. So, peak overshoot, I have the settling time, the rise time, and I have this error constants Kp, Kv, Ka and so on, right. And at the same time, I also have, if I have a frequency response like this is a Bode diagram of a typical second order transfer function. I will have a resonant peak. So, this is the resonant peak occurring at some resonant frequency, and these formulas we derived earlier. It will also have a bandwidth, right, this one of, okay, this is a ugly looking expression, but I will just quickly tell you how to do it by hand. So, I start with a second order system which is omega n square plus s square plus twice zeta omega n s plus omega n square. Okay. Then I do the sinusoidal version of it, that T of j omega is omega n square over minus omega square omega n square plus 2 j 2 zeta omega, and then this s will be j omega. So, I will have another omega n. So, when I define the bandwidth, I look at this thing, right. So, at which the magnitude is about 0.7 times the magnitude at here. Okay. So, the magnitude of this guy T of j omega is 1 over square root 1 minus u square whole square plus 4 zeta square u square, okay, where u I had defined earlier also to be omega over omega n, right. So, first is how do you define the bandwidth or even the cutoff frequency, right. So, this is the frequency at which the magnitude of the response, now I am talking about the frequency response, not the time response, is 3 dB or below, right. And the bandwidth is then defined as this 0 less than omega less than omega b, right. Okay. So, how do we find this? We just look at, okay, take the transfer function and evaluate it to 1 over square root 2 in the absolute scale, or in the log scale you sec 20 log of t j omega should be minus 3. Okay. Then I will just skip the computations because it just kind of is just very manual, right. You could just do it by yourself, and then I can say that the bandwidth is related to zeta and omega n via this kind of ugly looking expression, square root inside a square root and so on. Okay. So, I will not ask you to differentiate this or anything like that, but we will just try to not even remember this formula, only to show that there exists a relationship between the bandwidth, which is essentially a frequency domain concept. It relates directly to omega n and zeta, which came from the time domain specifications, right. Okay. For a system to track inputs quickly, it must have a large bandwidth. This again comes from here, right. What is bandwidth is depending upon omega n and zeta, right. And however, sometimes it is not desirable from the noise perspective, right, because if I have a higher bandwidth, as I saw when I was just having a pure derivative controller, it was an all pass filter and it had the drawback of not dealing very well with high frequency noise signals, right. So, in practice we will actually look at trade offs between good and bad, right. Okay. Now, the MR or the resonant peak, it depends only on zeta. So, somewhere here and then you also have the formula for the resonant frequency. So, in this case, well, it has an exact correlation with MP. If I just draw MR, so look at these two formulas, right? They are kind of quite nice. So, MR is directly depending on MP, the peak overshoot in the time domain specifications is directly depending on zeta, nothing else. Similarly, the MR also has a relation. So, if I find an MR here which gives me a value, I could correspondingly find a value for MP. Right. Now, can I do it all the time? Well, let us just see that, right. The resonant peak only exists for these frequencies, right, and therefore, whenever I look at the correlation between MP and MC, just from here till here, right, from till I reach this 0.707, that is just because of this guy over here. Okay. So, for this guys, well, I can just see that there is a direct correlation between MP and MR. Okay. Of course, this is not defined for zeta equal to 0, right. And then this is really too much of a concern, not really, because the peak overshoot for zeta being greater than 1 over square root 2 is very small, right. So, for a given zeta, either the bandwidth or the resonant frequency can be used to specify omega n via this guys. Given this guy, I can compute these things, right. Okay. And therefore, the bandwidth and the resonant frequency influence the rise time in the step response. And of course, I can just based on the formula for the rise time, I can compute when will how is this related to the bandwidth or WR, larger the bandwidth, smaller is the rise time, and so on, could just be computed by just looking at these expressions here, right. So, this is my bandwidth and this one. Okay. So, the aim is not to introduce you to complex formulas which are difficult to derive and even words to by heart, but just to show that there actually exists a good relation between the time and the frequency domain things. And in your end-sem exam, whenever you take, or if you take this, I will give you all the formulas which are required for you. So, you do not really need to memorize formulas, you just need to know how approximately each of the formula looks like. Okay. So, what can we conclude based on all these things, right, that exact correlation holds for second order system between the time and the frequency domain specifications. For higher order systems, if there is a pair of dominant poles, then we can still use this correlation, right. And as said earlier, well, the frequency domain control design gives us a little more information than in the time domain. I will still very carefully use the word simpler, right. And of course, the specification in the frequency domain after design are translated back to time domain to verify if the time domain requirements are met or not. And again, for higher order systems, we may need to do the design through extensive simulations, but then these are not very important to us at the moment, right. So, a basic understanding of the second order system will give us good amount of intuition while we do this analysis for higher order systems, just based on some lots of experiments and simulations. Okay. So, what we have done so far is to have a qualitative analysis of both the integral and derivative components. We also saw what were the practical issues of realizability, then we saw actuator saturation and so on, and we had some good approximation of these components called lead and lag compensators, and we saw also how the performance specifications in time and frequency domain are nicely interchangeable. So, next we will see how to implement this or how to design this lead and lag compensators, especially find the value of k, find the value of z, find the value of p. So, these were the important things, right, when we were realizing those lead and lag compensators. We will do that using the time domain or essentially the root locus technique, and also the Bode plot technique, which is essentially a frequency domain technique. So, and that we will try and use lots of MATLAB, we will plot lots of things for ourselves, we will ask lots of questions before we come to a conclusion, and hopefully that would be a little more intuitive while we are using MATLAB. Okay, thank you.